using the residue theorem, we want to show the improper integral from minus infinity to infinity of 1 over 1 plus x to the 4 with respect to x is equal to pi times square root of 2 over 2. Now, that seems like an unlikely answer, so I'll go to the computer, calculate a Riemann sum. So, if we have the graph of our function, I'll go from minus 10,000 to 10,000. We're going to fill it with rectangles with base 0.01. Push it through. What comes out is 2.22. We know that's a good approximation for pi times square root of 2 over 2. So now I believe this. So how do we get it exact? For that, I'm going to use a line integral in the complex plane. So we're going to do the setup for the residue theorem. So what I'm going to need is, first, we're going to have a closed curve. Okay, it's only going to go around once. So here, we're going to go from minus r to r on the real axis. Then we're going to close it off by using a circle, okay, centered at the origin of radius r, and we just use the top half. Then I orient everything in the counterclockwise direction. Now, what the residue theorem says, okay, if our function is holomorphic in this region, except at isolated singularities, then we can compute this line integral just as 2 pi I times the sum of the residues at each singularity. And in this case, we're just going to have poles. So, what's our setup? Our first step, I'm going to want to compute the residues of the poles of our function in the upper half plane. Then, we're going to break our integral into two pieces. Okay, one part is going to be equal to, okay, the integral along the real line from minus r to r. The other part is going to be along the semicircle. Then, we're going to take the limit as r goes off to infinity, and we want to show that the integral along the semicircle is going to go to 0, which will mean to get the improper integral, we're just going to have to compute 2 pi I times the sum of our residues. Our first step is to compute the residues at the poles in the upper half plane. Now, function is 1 over z to the 4th plus 1. It's a rational function and it's reduced, so we can't cancel any further. That means only singularities that can have our poles, they're going to occur where the denominator is equal to 0. So our poles occur where z to the 4th plus 1 is 0, or z to the 4th is equal to minus 1. Now, we could solve this using de Moivre's theorem with n equal to 4. We find the polar decomposition of minus 1. We're going to have the modulus, okay, or the r is equal to 1, and then the angle is going to be equal to pi. So the idea is we go out by r equal to 1, and then just rotate by pi, and then we land on minus 1 on the real axis. Now, recipe for our new roots. The new modulus, take the old modulus to the 1/4 power, so we still keep our 1. For the new angles, take your old angle, add all multiples of 2 pi, and then divide by your n. So we get pi fourths, 3 pi fourths, 5 pi fourths, 7 pi fourths. Putting these together, our roots are going to be, okay, we have omega equal to e to the pi I over 4, then its cube, 5th, and 7th powers. Now, we plot these in the complex plane. Okay, they're all in a unit circle, and they're all going to live on a square. The check, okay, well, if you note, our original polynomial has only real coefficients, so its complex roots occur in conjugate pairs. So that's just the same as saying if we take complex conjugate, roots go to roots, and that holds up. Then, note also, if we send z to minus z, polynomial is unchanged, so that also preserves the roots. So if we rotate by 180 degrees, okay, roots are also going to go to roots. So that just checks our factorization. Now, we're only interested in the upper half plane. The roots that are going to occur there are going to be omega and omega cubed. So I want to compute the residues at those points. These poles are going to be simple poles. So the idea is we could just factor this out. Then you'll note, when we factor, we have 1 over z minus each of our roots. So all the exponents are 1, so the poles are simple. Now, to get the residues, okay, You could multiply by, say, z minus omega and then evaluate at omega, and that's perfectly fine, but you notice that's going to be a little bit messy. So a cleaner way to do this is to use L'Hopital's rule. So if I want the residue, say, at omega, what do? We're going to multiply by z minus omega. So that would do our canceling before, but the idea is to take the limit as z goes to omega instead of doing the straight evaluation. Now, if you notice, if we evaluate this at omega, we get 0 over 0. So L'Hopital's rule applies. Then, what does that say? Well, we can take derivative of the top, derivative of the bottom, and then try to evaluate again. So I do that, I'll have a 1 on top, and the bottom we get 4z cubed. So if we evaluate at omega, we get something that's perfectly valid. I'll have 1 over 4 times omega cubed, or 1/4 omega to the minus third power. In a similar manner, you could use L'Hopital's rule to get the residue at omega cubed. That's going to be 1 over 4 omega to the ninth power. If we put these in polar form, we have 1/4 e to the 5 pi over 4, 1/4 e to the 7 pi over 4. Now, we want to add these together, multiply by 2 pi I. Let's start by just adding the parts that are in the unit circle. So if we do this, I have omega to the 5th, omega to the 7th. We add them as vectors. So this sum is going to wind up on the imaginary axis, which means it's a real multiple of I. What's the real multiple? Well, where I've drawn this horizontal bar in, that's just the y value in the unit circle. So that's going to be sine of 5 pi fourths or 7 pi fourths. If we want to take this point, that's the sum, well, that's just going to be twice the distance. So we're looking at 2 times I times the sine of 5 pi over 4. That's going to give us minus square root of 2 times I. So we're going to take minus square root of 2 times I, multiply it by the 1/4, and then multiply by 2 pi I. When I do that, I get pi times square root of 2 over 2, as expected. Now, if this isn't your style, that's fine. You'd instead take our points in the unit circle, put them in rectangular form. So you'll get something like this. And that's going to work out to give you your answer also. Now, since we have this, we can now focus on the line integral. So we have our closed curve here. We want to break that up into 2 pieces. One part that we're going to want to go to our improper integral. The other part we're going to want to go to 0. Finally, I want to show if I take the line integral over the semicircle, I let r go to infinity, then our integral is going to go to 0. For the first step, I'm going to parameterize our curve. So it lives on a circle, radius r, centered at the origin. Can use z of t equal to r e to the it. Since I only want the top half, I'll choose t between 0 and pi. So it's going to start at r, travel counterclockwise, and then stop at minus r on the real axis. That also has the correct orientation. Now, with the parameterization, we're trying to find a bound for the modulus of our function. So where we have a z, we're going to put in r e to the it. That's going to give us this term here. Then our claim is going to be that we'll have modulus of our function on the curve between 1 over 1 plus r to the 4th and 1 over r to the 4th minus 1 if we let r be large enough. Since we're going to take the limit as r goes off to infinity, we'll hit large enough eventually. Now, how do we use that? Well, we have resultant states. If we take the modulus of a line integral, that's going to be less than or equal to the maximum of the modulus of our function on the curve times the length of our curve. So in this case, we have the upper bound of 1 over r to the 4th minus 1. We're going to take that, multiply by pi times r, the length of the semicircle. Then you note, if we take the limit as this goes off to infinity, we're going to go to 0, and then that's our result. To show the claim, we instead prove the equivalent statement that the modulus of 1 plus r to the 4 e to the 4 it is between r to the 4 minus 1 and r to the 4 plus 1. So all we've done here is move the terms from the denominator to the numerator, switch the order of the inequalities. Now, for the geometry, the modulus is just going to be the distance from our point to the origin. So we're going to interpret this in terms of radii of circles. Now, to start, if we take all points of the form r to the 4, e to the 4it, we have a circle centered at the origin of radius r to the 4. If we add 1 to each of these points, that 1 is going to go into the real part, so we're shifting everything to the right by 1. So now I have a circle centered at the point 1. Okay, 2 other points in the circle, 1 plus r to the 4th and 1 minus r to the 4th. Now, if I draw in the circle centered at the origin that goes through 1 plus r to the 4th, okay, we'll have this picture here. So the radius is r to the 4 plus 1. We know the distance from the origin to any point on our blue circle, the original circle, it's going to have to be less than r to the 4 plus 1. So that's going to be the second half. Okay, the modulus here is less than or equal to r to the 4 plus 1. If we draw the circle on the inside, so it's going to be the point that intersects at 1 minus r to the 4. Okay, we're centered at the origin. So the radius there is going to be r to the 4 minus 1. Okay, note here what this is saying for the blue circle. Okay, the distance from any point to the origin is going to be greater than the radius of the circle on the inside. So it's going to give me that this modulus is greater than or equal to r to the 4 minus 1, and that's our claim.